Yeah, actually, we are discussing about mineralogy part. In a mineralogy part, we have seen still study that is about mineralogical properties, how we can identify the mineral when we see the with naked eye. There are various types of properties we have seen. The form, how it is look like, the structure, streak, cluster, cleavage, fracture formations, and forms, and there are different formations like pseudomorphism, polymorphism, isomorphism. All we see that. Specific gravity also we have seen. And today we are going to discussing about some rare properties. The rare properties we have studied, just we discuss outline only. Those properties will see the in different minerals. Some variety of minerals are having variety of properties: phosphorescence, fluorescence, fusibility, magnetism, electricity, etc. Phosphorence, some substances emit the light when they undergo in a heating or rubbing, even on exposure to electric radiation, such metals exhibiting the own properties. And the diamond fluoride display phosphorescence under different conditions. The diamond and exposure sun it become a phosphorescent. The phosphorescent means if the light, if it is a fall on that one directly, it is emitting the light. Or the property it has diamond such type of minerals. If it is expecting the same, or else if you go to the fluorescence, in a fluorescence of minerals, yesterday I told you the fluorescence. Fluorescence it is yeah. Fluorescence, it will be displaying the mineral phosphor phenomena. It is known as the fluorescence. It's absorbing the light and it's emitting the light. In a dark place, if you keep the fluorescent minerals, it's exhibiting the light colors, or it's exhibiting the different colors. Example for yesterday, I told you that is a fluorite. If you see the fluorite in a dark night, or if you keep that fluorescent mineral, if it's keep in a dark place, it's exhibiting the blue color of the light. It is coming from the fluorite. And again, some feasibility it is also some feasibility of minerals. When we are heating the minerals, if you wanted to eat or if you wanted to heat the minerals, those the materials, whatever it is fused together, either a temperature or amount of heat it is required, and it's melting. It's very easily to getting the flame. So example for stibnite. And actinolite. There are categories for stibnite, chalcopyrite, almandine, actinolite, orthoclase, and andesite. These minerals are very good conductors for flame and easily to melt at a melting point. It is required some temperature. Magnetism. Some minerals like magnetite are highly magnetic. Generally, with minerals containing the iron ore are more magnetic, but monazite, which is a lacks iron, it's also the magnetic but very weak. Quartz, feldspars are non-magnetic. And electricity. In electricity, in some minerals, electricity charge may be induced by heating, and at another minerals are the same. It is possible only an application of pressure on them. Tourmaline quartz belongs to the first type where the minerals it's known as the both pyroelectricals and piezoelectrical properties which are having. And the piezoelectrical property it was first detected in 1881 by the Pierre and Jacques Ory. It is known as a it is known by the post the First World War that sound waves are produced by submarine and it can be detected by the piezoelectric side and by the employing the quartz. Quartz. And next coming to the remaining structures in Neso, Soro, Cyclo, and Ino silicates. In Ino silicates, Neso, Soro, and Ino silicates, here the maximum is consisting of olivine garnet groups will become under the nesosilicate. Epidote group, it will become under the sorosilicate. Tourmaline, it is as a cyclosilicate. The remaining pyroxene family and the amphipoles family were considered under the inosilicate. First, we will see the nesosilicates. This group of minerals, which are consisting the independent the tetrahedra of SiO4. So here, it's a association with the regular minerals or crystal structures. We will see the silicon and oxygen tetrahedrons of nesosilicates. Maybe it's not polymerase. So that the silicon and oxygen tetrahedron of nesosilicates are not polymerized. They link to one another only by ionic bonds, which are interstitial pattern. If you see the result of isolation of tetrahedral groups, the crystal habits of these minerals are typical equidimensional, and so that prominent cleavage directions are not present. the size and the charge of the interstitial cations, which are largely and determine structural forms of the nesosilicates. So here, some specific gravity and hardness is also playing the very important role. The best example for this one, Alvin groups. Alvin group of minerals and as well as garnetic group of minerals. The Alvin group of a mineral, it's all having the orthorhombic symmetrical property. And structurally, it's consisting of SiO4 independent structure. And the tetrahedra is linked divalent atoms in octahedral coordination. And this family is consisting of an isomorphous series of nesosilicates with a general formula that is known as a R2 plus 2 SiO4, in which R is equal to magnesium and iron. The color of alvin is also showing the shades. We know that alvin is always showing a green color, or plain green, or play gray, pale green, olive green. Sometimes we can able to see this is grayish. The streak, it is you see the streak, it is a colorless. Because of the hardness, it is a very high. So that the specific gravity is also very high. So that we are unable to get streak. It's the colorless means white. Something. The luster, it is a look like as a vitreous. Fracture, it is looking as a conchoidal fracture. And the hardness, maybe it is going to be around the 627. So that is the reason we are unable to get a streak color. The essential minerals of alvins, it is a present, very present. It is yes. It's known particularly in the rock of peridotite. And dunite is also occurs in a basic igneous rock like alvin gabbros and basalt. The variety of a forestite is formed by the metamorphism. The magnesium and end member of sericite, it is the sericite, which is Mg for SiO4, and the iron end member is the phthalate, that is Fe2SiO. It's between the alvin, that's the MgFe2SiO. Yeah. The garnet group. In a garnet group, the origin of the word garnet, it's coming from the Latin, that's granitus. It means used like it's looking as a grain. In olden days, the garnets were the first was used the precious stone or as ornamental stones, and it is pleasing to beautiful shades of the colors, luster different we can able to okay. And even though they are very characteristics of a metamorphic rock and found sometimes we may found in igneous rocks and in sediments and detrital veins. These are all called as isometric cubic silicates. Isometric cubic silicates. That is in an igneous rock, the chemical composition of this one is bearing in a general formula. The formula, it is X3Y2SiO4 or else X2Y3O4 or else we see that is as whereas X means it is indicating as a calcium, magnesium, iron, or sometimes maybe it is manganese, manganese also. Y stands for, that means Y it is indicating as a secondary minerals of elements like with inclusion, iron, aluminum, chromium, and titanium. the species, the species and the formula. Almondite. The almondite, the formula it is FeAl2SiO4 taken price. Taken price as per that it is going to form as a mineral. Next one is pyrope. Pyrope Mg3Al2SiO4 taken price, and specify right. It's Mn3Al2SiO4. Grapholite, it's Ca3Al2SiO4 taken price. Andradite, Ca3Fg2 SiO4 taken price, and Eurovite, it's a chromite mineral. Specifying it is a manganese metal, and grapholite aluminum calcium related, and right it's iron related. And Eurovite, it's a Ca3Cr2SiO4 is taken right time. And very rarely does any natural garnet approach formula is mentioned here. And it is a large scale atomic substitution. So that the name of any species goes by the component. It is present the greatest amount. The substitution takes place between the andradite and the grapholite, and also between the pyrope, specifying, and almondite. The garnet crystallizes in a cubic system, which are very fairly hard, but they are brittle. They may be broken into the small cubic grains. The alteration effect on a garnet, at least, the specific gravity, the specific gravity, it is high. The specific gravity, it is high. When we see the fracture of this one, it is either maybe it is even or subconchoidal. Under a microscope, these all are having the isotopic nature. Isotopic nature. So there are seen in a rounded and a sub-rounded crystals with a characteristics that are having the crack but lacking of a cleavage. The garnets are used in abrevation and as a gemstones also. Next, coming to the sorosilicate. In a sorosilicate, these minerals are containing the two sets of SiO4, and the general formula it includes that X2Y3Si3O12 OH twice OH. That means hydroxide substrate. It's two sets of SiO2 tetrahedrons which are joined by one shade of ethical oxygen. A silica 2 Oxygen ratio, it has a 2 is to 7. 2 is to 7 in the sorosilicate. It's consequently present in their structure. More than 70 minerals belongs to the sorosilicate group, although most are the very rare. Only the members of the epidote group, that may be Vesuvanite, uh, in the epidote group, it's are common. In a both independent SiO4 and the double Si2O7, the groups are incorporated into the epidote structure. Yeah, the most of the minerals which are occur in a metamorphic rock, allanite, we found the allanite. It's in a igneous rock such as the granite and the pegmatite. Joycites and the clinojoycites, which are peculiarly identical in chemical composition with anarthite. They exhibit the different colors. Their hardness it is a 6 to 7, and specific gravity is a 2.7 to 4. The cleavage it is a markedly present in some members parallel to the basal plane, that is shown as a 001. The color it is the luster of a color it is a bit. Yeah, the common minerals are given here. Joycite, Ca3Al2, SiO4, second rise OH, Ca3Al2, SiO4, second rise OH, which is a clinojoycite. And epidote. In epidote, it is also calcium associated, but the additionally iron will be joined here along with aluminum. Ca2Al, Fe3, SiO4, second rise OH, allanite, CaFe2, AlFe, SiO4, second rise OH. This allanite it is as a radioactive mineral. Here, the cerium, it was there, and it is creating the radioactive fractures on a surface. Yeah, next coming to the cyclosilicate. In a cyclosilicate, silica and oxygen tetrahedrons which are linked into rings. It looks like a cycle system, and which have an overall Si is to O ratio of 1 is to 3. There are three closed cyclic configurations with the following minimum formula: Si3O9, Si4O12, and Si412. The rare titanosilicates and bentonite BATI Si3O9 is the only mineral that it is built with a simple Si3O9 ring. Axonite. The axonite, this axonite mineral is having the calcium, iron, magnesium 3, Al2BO3, silica 4 atoms, and oxygen 12 atoms, and it's containing SiO12 ring. Yeah, if you can see the thin section, if we if you see the under a thin section of this, the color which may be vary. The brownish and yellow, green, and strongly it's a pleocrite. It is seen as a subhedral grains or a triangular or a hexagonal cross sections may identify. The relief, it has a relief, it is very high and it has a uh, bright fingernails moderate to very strong. The relief means here the gap between the one grain to the another grain within a color. Actually, it is showing in a dark color. The property we can say it's relief. Alterations also we can able to see here. The alterations to mica or chloride. It is a notice in some cases optically which are negative and color some other striations. The absence of a cleavage and typical cross sections are very characteristic. The straight extension under the polarization. The straight extension, strong pleochroism, the maximum absorption of when light it is fall on this slide, it is at a right angle to the vibration planes for polars under the polarizer. The high relief it is also diagnostic feature. Yes, exactly. The relief it's a diagnostic property of a mineral. And the distinguished from the apatite by higher hardness, it may be differ with the beryl because of it's also having the higher hardness and density is also very high. By the beryl it has a very sharp striation and it has hemimorphous. The apatite by higher hardness, the different varieties fuse in a different forming. It's a greenish glass, insoluble in hydrochloride, which occur as an necessary mineral in igneous soil and metamorphic rocks such as granite, syenite, gneiss, and schist. It also occurs in a pegmatite. The brown magnesium rich in barite occurs in a marble. In sediment, it occurs as a rounded grain. It is used in the industries due to the pleochroic or piezoelectric property which are having in these type of minerals. Yeah, there are certain varieties which are occurring in Brazil, USA, England, and which are used for a precious or gemstone. Yeah. The variety of minerals are given here. It's a scroll, iron rich block tourmaline is dravite. It is a magnesium rich brownish variety. Rubellite. It is a colorless red or a pink variety of tourmaline. which is used as a precious stone. Chakrate, a blue variety. Elbite, colorless green, blue or yellow variety. Uh, Indicolite, indigo blue variety. The Brazilian emerald is the green variety, and Brazilian sapphire, it is a Berlin blue. At the chemical composition of tourmaline, NaMgFe taken thrice, Al6 and OH4, BO3 Si6OH, iron of silicate. In iron silicates, which are called chain silicates also. So here there are two groups, namely single chain and double chain. The single chain silicates are represented by pyroxenes, and double chain silicates, which are represented by the amphipoles. Pyroxene family. There is an intimation, the relationship between the number of pyroxene group with reference to their physical properties, chemical composition, and their structure also. Yeah. Okay. The physical and chemical properties and composition of the structure. The crystalline orthorhombic and monoclinic systems, they are essentially metasilicate, and there the crystal composition it may be expressed by the general formula of that X, Y, Z taken at 5, W2O6, whereas X, Y, Z and W, we know that the different types of elements are identically in ionic ready. The structure, if the structure they can also replace each other. The X stands for calcium, sodium, and Y stands for magnesium, iron, manganese, lithium, zinc, sorry, and Z for it's again aluminum, iron, titanium, and wolframite. Usually, we know that silica we can be replaced partially by a aluminum. The pyroxenes are typically characterized a prismatic cleavage, and some the parting it is not noticed. Twinning is a common. The range of hardness from the 5 to 7, and the specific gravity from 2.8 to 3.7 is usually dark colored blue. It's making showing the white, blue, or yellow colors. The altar is already readily to chloride and amphipoles, change as a amphipoles. And there are some essential constitutions and many English and maybe sometimes it's occur the metamorphic works also. The agate and physioelectric, which are the commonest minerals of the pyroxene group. The soda of The the agate and physionite are commonest minerals in the pyroxene group. The soda pyroxenes are jadeite and agarine. Here there are mentioned some principal composition of minerals. Enstatite, it has orthorhombic pyroxenes. Enstatite, it is indicating as a MgSiO3. And next one, it is a hypersine. MgSiO3 monoclinic pyroxenes. The dioxide, it is showing as a magnesium Si2O 6 Heidenbergite. The Heidenbergite it is indicating as a calcium iron silicate. That's Ca Fe Mg sorry. Yes. Heidenbergite, it's a CaFeSi2O6, agate, physionite, jadeite, agarine, and spodumene. The spodumene is a lithium associate. This is important. Spodumene. Next, coming to the enstatite for a detailed study of this one. Enstatite in an orthorhombic prismatic or a massive form. In a massive form, the hardness 5 to 6 it has. This looks like into a white, gray, pale, green to yellow, green in color. The streak, it is showing the streak, it is a white because of the hardness, it is a very high here. So that automatically it is showing whitish, white color. Vitreous luster. The vitreous luster and it has uneven fracture. The chemical composition of this one MgSiO3. In thin sections, it shows the non-pleochroic. The parallel extinction is occur in intermediate and basic igneous rock. Next, coming to the hyperscene. In a hyperscene, it has an orthorhombic system, and the crystals formed very dull. Cleavage, it is a very perfect. So, sorry. Hardness, if you see the hardness, that's the 5.526. It is looking into the brownish green and dark brown to black color also. The fracture, it is uneven fracture. Chemical composition Fe, Mg, Si, O3. In instead, only just we are adding the iron molecules. It is iron molecules. They added that one that will be converting as a hyperscale. In a thin sections, it is looking as it is pleochroic. It's a pale reddish, and the straight extension it has, and it is occurs in a basic igneous rock. And going to the diopside. In a diopside, in a diopside, monoclinic, prismatic, or massive, or a granular form. Hardness it is a 5.6 to 6. The color, it's a colorless actually, and it has a light greenish streak. It's a white or a gray. It is also having the uneven fracture and the perfect cleavage. And the Miller index is showing the 110. The chemical composition it is dioxide CaMgSi2O6. CaMgSi2O6 in thin sections, distinct in a cleavage, parallel extinctions it has. It is occurs in a igneous rock. Agate. Agate it is a monoclinic or a granular or lamellar massive form. It has 5 to 6 greenish to brownish black color, colorless streak, uneven to even a conchylic fracture, vitreous to resinous luster it has. Chemical composition is the CaMgFeAl taken twice, and again it's associated with alumina AlSi2O6. In thin section zoning, you can see that the straighter symmetrical extinction, and it can occur in gabbros, basalts, andesites, uh, dolerite, and diorite rocks, etc. etc. If you see in a amphipoles stamp, it is the relationship between the amphipoles and pyroxene. With the reference, as per reference, it is depend on the crystallography and chemical composition. And this also, we will observe the physical properties also. Yeah. The amphipool is a group of ionos silicate minerals forming the prism or needle-like crystals, and it's a composition of a double chain tetrahedra. The yeah. When you go into the mineralogy, amphipoles crystallize into the two crystal systems. It's a monoclinic one, and second one it is orthoram. In a chemical composition and general characteristics, they are similar to the pyroxene. The chief differences between the main differences between the pyroxenes and the amphipoles contain the essential hydroxide, hydroxide, and the halogens of the halogens of the same, or else the amphibolite is not derived to the metamorphosed of morphic rocks. It is considered as a metamorphic rock. They like pyroxenes, they are mostly metasilicate. The structure of meta amphipoles it's based on double SIA 4O11. The chain parallel to the C-axis, and instead of that, the metasilicate ratios of SiO4 O12 The chemical composition of various members of this group. In general, we can express the formula. XYZ is a 7 to 8 times in the SiO4O12 for its taken 5. Where here XYZ means X it is indicating as a calcium, sodium, and Y it is recognizing as the magnesium, iron, and Z it is recognizing as a iron. Hydroxyl group is always present in the structure. The ratios, we see the ratios also. Ratios also very important. The ratio between the Si and O, that should be actually it is a 4.11. And previously we see that is as a 4:7. Here it is a 4.4:11. The amphipoles where the pyroxene, it is as a 1:3. Aluminum is replaced by the silica, and hydroxides, that the OH is replaced by the fluoride. And sometimes potassium it is also present in a small amount along with the calcium, sodium, magnesium, and iron and the manganese. These two are interchangeable elements, and this is a limited substitution between aluminum and iron. Based on the chemical composition and the crystal system, the various species are grouped in different series. Orthorhombic amphipoles. It's one orthorhombic amphipoles. Second one is the monoclinic amphipoles. Third one is triclinic amphipoles. In orthorhombic amphipoles, it is the best example for this one, amphiphyllite. The chemical composition of this one, Mg, Fe, taken 7, and S8O22, OH, taken twice. Next, monoclinic amphipoles. In a monoclinic amphipoles, the cummingtonite series. In a cummingtonite series, cummingtonite, the chemical composition of a cummingtonite, MgFe7, Si8O22, and OH5. Grunerite. And it's also having the same composition, the similar composition would be there. And third, in a tremolite series, Ca2Mg5, Si8O22, OH taken 5. So in actinolite, it will be adding the measure of iron content. Iron content Fe 5. Next one is a Hornbender series. In a Hornbender series, it's a composition of all the major elements maximum: calcium, sodium, magnesium, iron, aluminum, and AlSiOH O22 and OH5. The sodium amphipoles series. In a sodium amphipoles series, glaucophane A is a glaucophane, that is a sodium 2 magnesium iron composition is three atoms. MgFe taken twice. Alumina iron is taken twice. Si8, O22, and OH taken twice. Ribokite. In a ribokite, the chemical composition of ribokite, it's a sodium, iron, Fe, again iron, SiHO22, OH5. And next one is ferrocite. The chemical composition of this one, Na3Mg4AlSi8O22OH5. And coming to the triclinic amphipoles, it is a calcerite. It's a silicate of iron, titanium, sodium, and aluminum. There are some minerals mentioned here. Anthophyllite, the first one, it is anthophyllite. In an anthophyllite, it has a orthorhombic system and massive fibrous form, perfect cleavage, and the hardness, it is a 6. White or a gray, brown or a green in color. The streak white and the vitreous, it is in luster. Chemical composition of anthophyllite, it is a MgFe7, SiHO22OH5. In thin sections, we see this is a colorless to the pale yellow color or green color, pale green color. So straight extension it has, and it is occurred in a metamorphic rock, anthophyllite. Tribbolite. Tribbolite, it has a monoclinic system, systematic and columnar form, perfect cleavage, uneven fracture. Hardness, it is about 5 to 6. Color is white. If you see the streak, it is also looking into the white. Cluster is a vitreous cluster. Chemical composition of this one, Ca2Mg2Si8O22OH taken twice. In a thin section, it is looking as a green color, diophrite and oblique extension. The colors in a low and a medium grade of the metamorphic. Next one is a hornblende. Hornblende, it is also looking as a monoclinic and prismatic. It is also having the perfect cleavage, that is a 110, and uneven fracture. Hardness, it is a 5 to 6. Black or a dark brown or dark green in color. It is also showing the colorless streak. Cluster, it is a vitreous cluster. The chemical composition of this one, CaNaMgFeAl, taken 7 to 8 times, and it is alumina Silicate, AlSiO8 and O22H. If you see this one in a green, thin sections, it's looking as a green or a brown color. The difference between the pyroxenes and amphiboles here mentioned. The pyroxenes always appear as a sharp and stout of crystals, whereas amphiboles have a tendency to develop into a long prismatic and fibrous or circular forms. The cleavage, which reflects the internal chain of geometry, it is very prominent in the members of both the group and the prismatic fractals to the axis. And another one, it is the basal sections pyroxenes are light sided, but the amphiboles they are six sided. Amphiboles yield the water is closely to on a heating. As for that, the pyroxenes it's angled about 48 degrees, and the oblique section is extension showing about 16 degrees in amphiboles, where the same we can see it is in 48 degrees in pyroxenes. The amphiboles which are in near water, it's a closed tube on a heating, but not the pyroxenes we cannot do. Yeah, I'm stopping here and we'll continue tomorrow. Tomorrow we'll finish the silver. Thank you.